Okay, so leaving off from last problem, we have discovered that every rhombus is a parallelogram, which also implies that everything that we know that is true about parallelograms must be true for a rhombi. In particular, this huge theorem here, stating that the opposite sides of a parallelogram are equal, the diagonals bisect each other, and that the angles are congruent at the opposite ends. In fact, part A can be, even in the case of a rhombi, extended so that AB equals CD equals AD equals BC. They're all the same side. So that means any theorem that we learned in here can be applied to rhombi. In addition, we can also apply the same formula for area, since that is true of parallelograms, and all rhombi are parallelograms. Now, let's use this idea in problem 8.14. ABCD is a rhombus such that the diagonals AC and BD have lengths of AC is 30, BD is 16, and wants us to find AB and the area of ABCD. So, let's look at the diagonal AC. In the theorem that we were just looking at, we learned that parallelograms, in parallelograms, the diagonals bisect each other, which means that AC is bisected at this point, I'll call it M, which means that AM is 15 and MC is 15. BD is 16, so that means that DM is 8 and BM is 8. Now it would like us to find AB and the area ABCD. So, how can we figure that out? Well, we don't know what AB is, but we do know that in a rhombi, all the sides are the same. So I know that AB is the same as BC, is the same as DC, is the same as AD. And we'll call that value lowercase x. Now, this should show me, if I fill in all these values with x, that something immediately pops out, which is the fact that we have triangle congruence. We have side-side-side congruence, where each of the four triangles in the rhombi, ABM, BMC, CMD, DMA, they are all the same triangle by side-side-side congruence. So, let's state that out. Triangle ABM is congruent, ABM is congruent to the triangle. Now ABM goes from A to B to M, so the last side we will go through is that side of 8 to reach M. If I follow the same pattern over here, that would mean I have triangle CBM, since that goes through the 8. So CBM is congruent to triangle, following the same pattern, CDM, which is also congruent to triangle ADM. And this is all side-side-side congruence. Now, that is interesting, but it really doesn't help me find the side x. So, how can we continue in this problem? Well, I know that the easiest way to find the sides of a triangle is to get a right angle. Now, is there any clever ways to get a right angle out of this problem? Well, according to all these congruence theorems, I know that the angle at AMB is the same as the angle at BMC, is the same as the angle at CMD, is the same as the angle at DMA. And if I put them all together, they add up to 360 degrees. And I have 4 of those measures. I'll call them Y. So angle Y. So that means that angle Y plus angle Y plus angle Y plus angle Y all come together to give us 360 degrees. Note, if I was a little bit more clever, I could have just said that 2 of the angle Y would be 180 since they're on a straight line, but whatever. We'll get the same result either way. Now, that means I have 4 of the angle Y's in total. So 4Y equals 360. Divide by 4 on both sides. And we get that the angle at Y is equal to 90 degrees. So it turns out that angle at Y is really a 90-degree angle. And based on how I drew the diagram, it doesn't really look like it, but we have shown that all these angles are 90 degrees, meaning we have right triangles. Now, how can we use this to solve the problem? Well, now that we have a right triangle, and we know that like the side AM has to be 15 and BM is 8, it's just a matter of using the Pythagorean theorem to get the rest. So let's find x. We have 15 squared plus 8 squared equals x squared. 15 squared is 225. 8 squared is 64. Now 225, 20 and 60 is 80. 5 and 4 is 9, so that's 289 equals x squared. Now to find what x is, we would have to take the square root on both sides, and by doing that we see that x is equal to 17. Okay, so now we have found the first part to our problem, where each of the sides has a length of 17. Well, what can we do from here? Well, just like a parallelogram, a rhombi has to be able to, we have to be able to find the area by the base times the height. But finding the height might be just a little bit too much for me to do, especially since we have 4 right triangles and they have equal areas since they have equal sides. So if I find the area of one of the triangles and multiply by 4, then it should be easy to get the total area. So I'll just say that 4 times the area of AMB is equal to the area of ABCD. Now, what is the area of AMB? Well, that's going to be 1/2. The base we could say is 8. And the height we can say is 15. Now, going further, 4 times 1/2 is just 2. Times 15 is 30. So we have 8 times 30. Well, 8 times 3 is the same thing as 240. So 240 must be the area of A, B, C, D. And that is it. Again, the common link with all of these problems, all quadrilateral problems, even the ones yesterday, trapezoids, are really just triangle problems in disguise. This is a common theme we will be seeing for the rest of the year and that we've seen previously. Triangles are, you can think of as the simplest shape. And all other shapes, besides like circles really, can be thought of as different triangles put together. And by breaking them down into triangle problems, we take complex shapes. Later we'll get to stuff like dodecagons and tetrahedrons and stuff like that, and find out that it's still just a bunch of triangles put together. And because of this, they will always be able to be solved by the same exact techniques that we learned in the very beginning of the year.